Just wanted to show you some kind of structural engineering marbles that have been recognized globally. For example, this one here, this structure is pretty famous. That's actually Palm Island in the Dubai, and then we have this structure here, which is basically Museum of the Future. Then we have the Eiffel Tower, we have the Burj Khalifa. So these are really pretty good and enormous projects in itself, and they have their own share of challenges as well. So they have been actually recognized as some of the structural engineering marvels globally. And then obviously, like India is also not really taken a backside in that case. I mean, we do have some structural engineering marvels in India as well, right? For example, we have the Lotus Temple, we have the Sardar Vallabhbhai Patel, which was actually erected pretty recently. We have Taj Mahal, we have Bandra Worli Sea Link, the Chenab Bridge, the Howrah Bridge. So they are really good and they're actually marvels in their own aspect. So, and the thing is, like, to make sure, like, these projects are kind of successful. So as I said, like, we need to use some softwares in order to make sure, like, whatever, because we need to study, like, what's the response of these buildings or structures based on the or the loads that we kind of apply to them. Because, for example, if it's a tall building, in that case, obviously we need to make sure, like, it's able to withstand wind load, because tall buildings typically are sensitive to wind load, versus if it's a short and stiff building, it could be seismic that's going to govern. So how do we take care of all of that? So for that, we actually need to use different softwares that is available. So that the software that we typically use in the industry are, like, some of them are listed here. So pretty common ones, for example, ETABS or maybe SAP 2000, Perform 3D. So they are all basically CSI products. So CSI is actually a very popular company in the field of structural engineering, and they have a bunch of tools that they have available, and then we can use them for different purposes. For example, ETABS is typically used for say a building type structure, but the SAP is used more for like a 3D non-building type of structure, be it stadium or whatever. And then we have Perform 3D, which is typically used for performance-based design and things like that. So in addition to CSI, there are like other companies as well. For example, Bentley, they have their own products like STAD, which is a very popular tool in India as well, STAD Pro. And then we have RAM S Beam again, which is a product of Bentley. And then we have analysis product by Autodesk as well, which is Robo Structural Analysis. So that's another really popular software as well, which is, I think, used mostly in European countries. And then we do have ANSYS and Abacus, which is used more for, like a research kind of field where, or maybe if it's a shell structure where, SAP or ETABS may or may not be able to handle. So in that case, people actually go for softwares like ANSYS and Abacus. So the point I'm trying to make here is, like, we have this, wide variety of software which is used in the industry for different purposes. So that's that. So most of these software are actually used for analysis and design of structures, but then ultimately whatever design has been done, that has to be like erected on site, and for that to happen, all of these design information has to be translated into the language that we typically speak, and that is drawings, right? So in addition to the analysis and design structures, we also have drafting or generating the engineering drawings. So some of the popular ones are, for example, Autodesk Revit structure, and then Autodesk AutoCAD. So they are really two stalwarts, I would say, in terms of engineering drawing production tasks. And then we do have some other kind of softwares, for example, Rhinoceros. That's another software that is typically used if your structure is kind of complicated in terms of geometry. So in that case, architects also tend to use Rhinoceros as a software. And then we have some plugins like Grasshopper or Dynamo, wherein you can actually programmatically do a bunch of stuff. So what I talked about before was the digital workflow aspect, right? Where you could actually make sure like two softwares actually talking to each other. For example, if you have to transfer any data from Autodesk or Revit to, say, ETABS, in that case, Dynamo would come into picture, and then Grasshopper would come into picture, where Dynamo is like a plugin for Revit, wherein we could programmatically control whatever is happening in Revit. And then similarly, Grasshopper is another plugin for Rhinoceros, where we could actually programmatically control stuffs in Rhinoceros software via Grasshopper. And then this Grasshopper is kind of flexible in that way. Like, it could also talk to ETABS or other analysis softwares, for example, SAP as well, for that matter. So these are the few kind of plugins here which kind of bridge the gap between the engineering softwares and the drawing softwares. So that was all in terms of the softwares which are typically used in the industry. So I guess that being said, we can actually now get into some of the technical aspects of what the topic for today is, right? So we can actually start with this. So I mean, as I said, like, whenever we are working on a structural engineering thing, so that means first of all we need to make sure we need to understand, like, what kind of material are we using, and we need to make sure, okay, we need to completely understand how does that material behave. So for that, the kind of the the main principle there is, the stress strain curve, or the basic mechanics that we have been studying from early on in our mechanics classes, even in early school days as well, wherein like there's this terminology known as stress, and then we have strain. We have Hooke's law, which kind of relates stress and strain, right? So that's what we have studied, where we say, okay, stress is, so basically whenever you deform any material, in that case, a deformation means there is strain. So whenever there is strain, there will be a stress which is developed in the structure. So that's what this says. So stress developed in a structure is kind of directly proportional to the strain, which is epsilon here. And this linear proportionality is actually valid only within elastic limit of the material. And then beyond that, it's actually going to be in an inelastic zone. And then we are going to actually take a look at that in the next slide about that. So this is kind of the basic principle that we always need to be aware of whenever we are working on a structural engineering analysis. Like whenever there is deformation, there will be stress developed in the material, and therefore in the member. And then obviously, like since a member, for example, if you consider a beam that has to be made of a material, right? So the behavior of the beam actually would depend on the behavior of the material. So that's the reason it is very important to understand the material behavior as well. And we have like different bunch of materials available as of now, which is being used in the industry widely. For example, we have concrete, we have steel, we have fiber reinforced composites and things like that. And they have like their own applications. For example, concrete is very, very commonly used in India. And then we have concrete and steel, which is kind of used more or less equally in, in the US. And then we have, say, aircraft, which are actually made up of materials like aluminum and things like that. So they have their own requirements. For example, aircraft has to be lightweight, but at the same time strong as well. So they use a different kind of material, which is not really the scenario in case of buildings, because in buildings we actually typically use concrete or steel. So different materials have their own applications, and that's how we come up with the choice of what material should be used in which structure. But then we do have those basic mechanic laws for all of those different materials. This is a curve which I think most of us would be familiar with, which is the stress strain curve for mild steel. So what I'm trying to show here is like we do have those different behavior of a structure for stress and strain, and this is what kind of governs the material behavior and as well as the behavior of the member. So for example, here if you see, like this is mild steel, so that means that's actually very ductile. So that means we don't really have a very brittle failure or a sudden failure. So even after this material has yielded, which is say at point B, beyond that also it's there's not much increase in the stress developed, because there's not, that's kind of the strength of the material. But you still see a bunch, pretty high deformation in the material, and that actually kind of dictates its ductility. So this is kind of one important aspect of the material that we typically deal with in structural engineering. And for example, unlike concrete, wherein you won't really see this long kind of range for strain. I mean, once the concrete has reached this compression capacity, it just tends to kind of crush, and that's a brittle failure, which we typically try to avoid, because that's going to be a sudden collapse in the structure versus this kind of a behavior, right? So the thing is, so basically what I'm trying to get at here is like we need to understand the material behavior properly, and all of these are being tested on in laboratories and things like that, and therefore we come up with what kind of structures or members, or how the members are actually going to behave because of these kind of materials.